Hey there, OChem ninjas. Do you ever wish organic chemistry had a cheat code that would predict where a molecule would react? Well, here it is. Draw the second best resonance contributor. That's the one that fights for reactivity. It's your shortcut to Markovnikov addition, understanding why carbonyls are electrophilic at carbon, and nailing the regioselectivity of the Diels-Alder and the electrophilic aromatic substitution. No more memorizing lists. Keep watching. In 3 minutes, you'll be predicting reactivity for molecules you've never seen before. At its core, organic chemistry is a predictive science. The ultimate goal of organic chemistry is to take this molecule and this molecule and react them together and predict the product of that reaction. You can't do it through memorization. There are too many organic chemistry reactions to try and memorize every single one of them. Instead, we use the fundamentals that we learn in organic chemistry, plus some chemistry logic, to predict the outcomes of novel reactions. And we have some tricks we keep up our sleeve to help us out. One of them is the second best resonance structure rule. The second best rule says that the second best resonance contributor typically defines the molecule's reactivity. It's very subtle and very powerful. It will allow you to look at a brand new molecule and predict whether it will be a nucleophile or electrophile, and where, with ease. One of the first reactions you may have learned in organic chemistry is the Markovnikov addition to an alkene. You may have memorized some mnemonics like hydrogen likes its friends. I don't personally care for those types of mnemonics. They don't tell you why the pattern holds. When this alkene reacts, the pi bond will break, and either of these two carbons could act as a nucleophile to attack this hydrogen. Don't worry if you haven't covered this reaction yet. That's not the point of this video, but I do have a video about this reaction that I'll link to in the description below. How are we supposed to know which carbon will be the preferential nucleophile in this reaction? The second best rule. We can draw some resonance contributors of this starting material before we get to the mechanism that can help us figure out which side will be the nucleophile. I could break this pi bond and put these electrons onto the internal carbon as one of the resonance contributors. That would place a negative charge on the internal carbon and a positive charge on the terminal carbon. Or I could do the opposite, break the pi bond in the other direction and draw a different resonance contributor. If I examine these resonance contributors, I could rank them in order of their contribution to the resonance hybrid. The neutral molecule with the most bonds and fewest charges will be the first best resonance contributor. The resonance hybrid will look most like the first best resonance contributor, but we could also rank these other two contributors as number 2 and number 3. It's not about the negative charge. That carbon at least has a full octet in both resonance contributors, but the positive charge only has 6 electrons around that carbon and lacks a full octet. If we've learned about carbocation stability, we know that the carbocation would be more stable at the more substituted position. That makes the internal carbocation resonance contributor number 2 and the terminal carbocation resonance contributor number 3. If you need a refresher on ranking resonance contributors, I have a video that I'll link to down below. And this tells us everything we need to know to predict the first step of this mechanism. The resonance hybrid looks most like the first best resonance contributor, so chemists tend to draw the first best resonance contributor. But the pro tip says the second best resonance contributor typically defines the molecule's reactivity. It's like X-ray vision into the molecule where we can see the reactive sites. The second best resonance contributor shows us a buildup of electron density on the terminal carbon and a lack of electron density on the internal carbon. Since this molecule is acting as a nucleophile, it will react at the site with the most electron density. The second best resonance contributor tells us the terminal position is that site with the most electron density. When this molecule acts as a nucleophile, it will preferentially be nucleophilic at the terminal carbon. When we draw the curved arrows for the first step of this mechanism, the second best resonance structure rule tells us the excess electron density is on the terminal carbon. The pi bond will break, that terminal carbon will get to keep those electrons and use those electrons to attack the hydrogen, kicking out the chloride as the leaving group. I'm using the bouncing arrow notation here. If your instructor is not using the bouncing arrow notation, they should be, and I'll try and convince you why in a video I have linked down below. So you may already know we're going to get the Markovnikov carbocation and chloride is going to attack to give us the alkyl halide, but now the second best resonance structure rule proves to us why. In carbonyl land, many of our reactions involve protonating a carbonyl to add some kind of weak neutral nucleophile. We need to know where this molecule will be reactive. And using our Ninja pro tip, we can use the second best resonance rule to figure that out. To draw a resonance contributor of this molecule, we can break the pi bond, putting the electrons onto oxygen to draw the only other resonance contributor for this molecule. To predict the reactivity, we'll need to rank these first best and second best. Pause the video, see if you can determine which one is first and second best of these resonance contributors. The answer may surprise you. Did you get these backwards? You could make the case that this should be the first best resonance contributor because all elements have a full octet. You could also make a case this should be the first best resonance contributor because at least the positive charge isn't on an electronegative oxygen. Both of those are important considerations. It turns out having a full octet on all the atoms weights heavier towards the resonance hybrid than where the positive charge is. So the first best resonance contributor has the positive charge on oxygen, and the second best resonance contributor has the positive charge on carbon. When this molecule reacts, it will be an electrophile at carbon. So even though the formal charge is on oxygen, when this molecule reacts, the weak neutral nucleophile will attack the carbonyl carbon, and kick the electrons up onto oxygen. That gets us to the tetrahedral intermediate with the methanol added. And the mechanism continues from there to form the acetal. I'm not going to go through the whole mechanism, but I do have a video on acetal formation that I'll link to down below. The second best rule predicts this molecule's reactivity. In the Diels-Alder reaction, when these two molecules react with each other, their orientation with respect to each other is very important for the outcome. If you've already gotten to the Diels-Alder reaction, you may know about this already. But if you haven't, watch how the second best resonance structure rule will allow you to predict the product of this reaction even though you've never seen it before. I'm going to tell you at the outset that these molecules are reactive at these 4 positions. See if you can pause the video and draw the resonance contributors for these molecules that would predict which of these carbons are electron rich and electron poor. The OMe group is an electron donating group. We can use a pair of electrons on oxygen to push electrons all the way through to that terminal carbon. If you're not familiar with electron withdrawing and donating groups and how they modulate electron density in a molecule, I have a link to that video down below. This resonance contributor shows us as a negative charge on the terminal carbon, but we still need to figure out the charge on this carbon. We can get there with one additional resonance contributor, putting the electrons back onto oxygen, putting a positive charge on this carbon. So using our second best resonance structure rule, and perhaps knowing nothing about this reaction, we can prove that this carbon is electron rich and this carbon at the top is electron poor. For the other piece, we can use the carbon-carbon pi bond and push electrons up into the electron withdrawing carbonyl. Because the carbonyl withdraws electron density from the carbon-carbon bond, we get a positive charge at the terminal position. That's good to know, but I need to know the charge at both of these positions, so we can draw one additional resonance contributor, returning the negative charge to that position. These resonance contributors gives us all the information we need to know. You may be weeks away from learning the Diels-Alder reaction, but through resonance, you can tell that this carbon on the top is going to be electron rich, and this carbon on the bottom will be electron poor. That's very cool. We know that nucleophiles attack electrophiles. We know that negatives attack positives. So even if we've never seen this reaction before, we can make a pretty good case that this negative will attack this positive and this negative will attack this positive. And that the product of this reaction should be this ring system with 2 new bonds. And spoiler alert, this is the product of this reaction. We can use a second best resonance structure to find the partial charges on the appropriate carbons to predict which bonds will form in the product. Finally, we can look at the electrophilic aromatic substitution reaction. Again, you may not have gotten to this reaction yet. I will tell you, these reagents will add a single bromine atom to one of the positions around this ring. The problem is there are 5 open positions around this ring. How are we supposed to know where the new bromine will go? You guessed it, the second best rule. Nitrogen is an electron donating group. We can use that lone pair of electrons to push electron density into the ring to start drawing resonance contributors. With the negative charge inside the ring, we can move the negative charge on other positions around the ring. And we can continue going further around the ring. So through resonance, we've been able to add excess electron density to the ortho and para positions around this ring relative to the nitrogen. And it's very interesting. If you look at this resonance series, there are no valid resonance contributors that put the negative charge at either of these meta positions. We can keep going around the ring, but the negative charge will always end up at the ortho and para position. So when this molecule acts as a nucleophile, it has to do so from the ortho and para positions. The second best rule unlocks that view for us. I'm not going to go through the whole mechanism here, but the product of this reaction will in fact be the addition of the bromine to either the ortho position or the para position. So when you get stuck on an exam and you don't know where to start, remember the second best rule. It's the best kept secret in all of organic chemistry.
Thanks for watching. The best way you can support this channel is to let your friends know about these videos, especially ones who go to different schools. Help spread the word around the country. As always, don't forget to like and subscribe.